Hi, I'm Gerald Stevens, Director of Support and Education here at EAW. Those of us lucky enough to work in the professional audio industry do so for many reasons, but most of us have one thing in common: we love audio. Sound is a fascinating subject, and we should all strive to learn as much as we can about how sound behaves in our world. So we'd like to give you an opportunity to learn some of the fundamental physics that define the behavior of sound. The more you understand, the more effective your system designs will be. Now, just like Dorothy at The Wizard of Oz, we must start at the beginning. And for us, it starts with a look at how sound travels through a medium such as air. Now in this animation, the loudspeaker is represented as this piston, while the black and red dots represent air molecules. The piston moves forward, pushing the air molecules closer together, causing an increase in pressure. It then moves back, causing the air molecules to move farther apart, which is a decrease in pressure. Note that the red dots don't travel, but simply move back and forth. What travels is the change in pressure, which looks like waves. The distance between the high pressure peaks or low pressure valleys is called wavelength. The number of complete waves or cycles in 1 second period of time is the frequency. And the amount of pressure is represented on this graph vertically, illustrates level or loudness. The greater the change in pressure, the greater the level. My friend and colleague, Pat Brown from SynodCon, says that the answer to most questions in audio is, it depends. This is so true because most things in audio depend on time, frequency, and wavelength, and all of these are affected by the speed of sound. To understand how to calculate these things, we have to do a little math. But don't worry, it's pretty simple stuff. We start with calculating the speed of sound, which is primarily dependent on temperature. Now you'll want to get a scientific calculator so you can do these calculations along with me. If yours is a software version like this, make sure you have it switched into scientific mode. That way you can do the squares, the square roots, and logs, and those sorts of functions. So the formula for calculating the speed of sound is 49 times the square root of 459.4 plus the temperature in Fahrenheit. The metric version is 20.06 times the square root of 273 plus the temperature in Celsius. Now let's see what the speed of sound is here today. Here in my office it's about 72 degrees Fahrenheit. So we add 72 to our constant, 459.4 plus 72, and we get 531.4. Now we take the square root of 531.4 and we get 23.05. Now we multiply that by our constant, and we get 1129.55. So in round numbers, the speed of sound at 72 degrees Fahrenheit is about 1,130 feet per second. If we run the metric formula, we would find that that is about 344 meters per second. Now these are real good numbers to remember going forward. 1,130 feet per second, 344 meters per second. Now that we know the speed of sound, we can calculate the wavelength of any particular frequency. This one is very easy. You just divide the speed of sound by the frequency. So the wavelength of 1000 Hertz would be 1130 divided by 1000. And we find the wavelength is about 1.13 feet or 350 millimeters at 72 degrees Fahrenheit. If we double the frequency, we get half the wavelength. So at 2K, the wavelength is about 6 inches, or 175 millimeters. If we half the frequency, we get double the wavelength. So the wavelength of 500 Hertz is around 2 feet, or 700 millimeters. Now you understand why the answer to the question is, it depends, because the wavelength of sound waves depends on the frequency and the speed of sound, which depends on the temperature. And when temperature changes, the wavelength changes, and the time it takes for sound to travel from point A to point B changes. Get the picture? This is what makes audio system design so challenging. We designers and operators have to deal with wavelengths ranging from about 3/4 of an inch at 20K up to wavelengths In engineering terms, that's 3 decades of wavelengths. Compare that to someone working in radio that literally works with fractions of a decade. Tell them to design an antenna that controls radio frequency pattern over 3 decades of frequencies, or design an antenna that would control the pattern of a frequency with a 56-foot wavelength, and watch their heads spin around.